Bismillahirrahmanirrahim. Our FIP title is Smart Energy Meter. Actually, we have made an energy meter which is IT based. Our supervisor is Dr. Asim Samejo. I am Shabir along with my groupmate Muhammad Faizan. This is the outline of this presentation. First, we will discuss the introduction of energy meter, then the motivation, why we have chosen this project, and then the problem statement, and then literature review, aims and objectives, methodology, why 71020 IC, feature of SAS 71020 IC, and then the experimental results which we are getting on different loads and the applications and references. Introduction. What is an energy meter? Energy meter is a device that measures the amount of electrical energy consumed by different types of load at different places, means at any residence, business, or any electrically powered devices. And the loads could be uh, inductive or reactive, resistive also. We have designed an energy meter using ACS 71020 IC to measure active, reactive, and apparent power. Using this IC, we can also measure the RMS and instantaneous voltages and current and average voltage and currents also. So these IC have different, actually lot of features. Motivation. Existing energy meter only give us active or reactive power. They are large in size, costly. We are using AC71020 IC. This IC gives us, this IC make our circuit simple, compact in size, and the cost will be minimum. And the with the output are the we are getting, which will be get by using this IC, will be, and the energy meter which will give us energy, voltages, currents, active power, reactive power, apparent power, frequency, and power factor accurately. Actually, there are many things which we are getting after completing this project. Problem statement. Old-fashioned watt meter are the digital meters which we are using in our houses, give us only real power or reactive power, and they are large in size. They are very costly, having less features. Literature view. ACS Power 71020 power monitoring IC greatly simplifies addition of power monitoring to any power device. Actually, this simplifies the addition of power. And most energy meter only give us active power, but this energy meter we are going to make could also give us reactive power, apparent power used by different loads like motors, that is inductive load, generator, transformer, and operating power system respectively. Maximum demand of energy of a consumer will be indicated in the meter used by the consumer. Actually, this energy meter which we have made give us the demand. It represents or indicate the maximum demand of the consumer and in the meter. Actually, and we use energy meter for billing purpose, aims and objectives. The research aims to design a system of energy meter that can regularly measure and monitor the consumption of electrical energy. Our aim is to fabricate a single phase energy meter with the reduce the fabrication cost, and the third point, our third aim is to make it IoT based using Wi-Fi. This is the methodology of our project. Our circuit board, the meter is connected with the power supply to a 20 volt coming from the WAPDA, and the circuit board is also connected with the load and microcontroller. Wemos is using in the place of microcontroller, and the output to are displayed on the a serial monitor LCD, 16 by 2 LCD, and ThinkSpeak. Why we are using 71020 IC? We have studied different types, few ICs, and the first one is ADE 7757 IC. Second one is 5460 and CS5464. If we talk about ADE 7757, then this IC is a single phase active energy measurement devices. It has Solana TSOP package, and it is externally shut in. If we make an energy meter using this IC, then the circuit diagram will be complex. We need large set of auxiliary components. That is, if we talk about 5460 IC, then this IC is a simple single phase bidirectional energy meter measurement device, and it has 24 SOIC package, and it is also externally shunt. And if we make an energy meter using this IC, then we will need large set of auxiliary components. And the third one, CS5464, it is also single phase power measurement devices, and it has a 28 SOIC package. It can measure RMS voltages and current, active power and reactive power. It is also externally shunt. And if we talk about the circuit of this IC or this using this IC, if we made an energy meter, then the circuit diagram will be more complex, and we need large set of auxiliary components to complete this project. The third one, the last one is the ACS 71020 IC. It is the IC which we are using to make our energy meter. It is a single phase complete energy metering IC. It has 16 SOIC package. It has built-in built-in shunt minimal. If we talk about the circuit diagram of our IC, then the circuit diagram is small. We need a minimal set of auxiliary components and mere all types of power. The main feature of this IC is that it mere all types of power and RMS averages and all types of power. So this is the circuit diagram of ADE 7757. As we can see that the circuit diagram is very much complex. It has many resistors and many connectors and other components. This is the circuit diagram of 5464 IC. We can see that it also needs a large set of auxiliary components, including different capacitor, resistors, diodes, and many isolation devices, power supplies, autocouplers, and different things. This is the circuit diagram of CS5464 IC. This is also very much complex as compared to the circuit which we have made. This is the circuit diagram of our energy meter. Actually, we have only used these 5 resistors and the VMOS, and so this is a step down circuit. We are connecting 2 resistors, one of 1 mega ohm and a resistor of our sensing resistor is also used. This is the 220 line. This 220 line is connected with the first 4 pin of our IC. The first 4 pin are internally fused, and these 4 pins are also internally fused. And the second line of 220 volt is connected with load, and the load, with the help of load, it is connected with the negative input pin of our IC. These pins are used to sense the current. The 15 and 16 pin of our IC are negative input and positive input. These are connected with the step down circuit, and 15 sorry 13, 14 are VCC and ground, and the other 4 pins are communicating pins. These pins work on two protocol communication. This is I2C and SPI. They transfer data from the IC to the microcontroller. Here we can say this is the reinforced isolation. Actually, this IC has different layers, which made this IC more powerful. If the input or the volt becomes high, then it can be a high voltages. Features of ACS 71020 IC. These are the features of our IC. The IC is capable of AC key power measurements. It can accurately measure active rate and apparent power as well as power factor. It can also measure RMS and instantaneous and averages also for both voltage and current. It has high voltage and current withstand capability due to its reinforced isolation. It works on two communication protocols that are I2C and SPI communication. It is a user programmable. We program this IC using Arduino, and the bandwidth of this IC is 1 kilohertz. It has a current sensing range from 0 to 90 ampere. These are the bill of material of our IC. Actually, we are using different things. We have a ACS 71020 IC of one quantity, one switching supply, one microcontroller, that is VMOS, one resistor, one capacitor, sorry, 10 resistors, one connector, and two pin connector, two pin headers, and 16:2 LCD to display the output. So this is the pinout diagram and terminal list of our IC, that is ACS 71020 IC. The first 4 pin and the next 4 pin means 5, 6, 7, 8, 8. These pins are used for current sensing, and they are internally fused. 9, 10, 11, 12, they are communicating pins. They work on two communication protocol, that is SPI and I2C protocol. 13, 14, 15, 16 are VCC, ground, negative input voltage, and positive input voltage respectively. This is the schematic diagram of our energy meter. Actually, we can see that the 220 volt is connected with load, and the load is connected with the 5, 6, and 7 pins of our IC that are internally fused, and the second line of 220 volt is also connected with the first 4 pins. And the 220 volt is also given to the step down circuit, and the step down circuit is connected with positive and negative input of the IC. This is the step down circuit. This is the step down power supply. 220. It takes 220 volt, and it gives us 5 volt at the output. 220 volt AC and 5 volt DC. This 5 volt is given to the LED of the circuit, and the communication pins are connected with the VMOS with the help of resistors of 10K ohms, and the VMOS is connected with the LCD accordingly. This is the PCB board of our circuit. This circuit is routed on the Eagle software. This is the mild circuit. Uh, this circuit is fabricated in FabLab with the help of our FabLab assistant, Sir Nadir. This is a soldered PCB front end. We have soldered different components on the mild circuit. This is the AC710 IC, and these are the different resistors, and the VMOS will be connected on the back side of this circuit. This is the back view of our soldered PCB. Now these are the experimental results which we are getting. When we have connected 100-watt resistive load, we are getting VRMS. This is the output on serial monitor of Arduino, and these are the output on the LCD 16:2 LCD. We have got 219 VRMS, 0.47 IRMS, and 102 active power. Reactive power is zero because the load is not inductive, and power factor, so one power factor frequency is 49.7. This when we have increased the load to 200 watt by connecting incandescent light bulb, we can see VRMS is almost same, and the current IRMS have increased because we have increased the load on load end. So we will also get the reactive power with some increment. This, if we talk about the inductive load, we have connected 1000-watt motor with our energy meter. So we are getting VRMS 218.3. We can see the IRMS is largely increased because the load is very high, and the VRMS is decreased slightly because of the increase in load at the load side. This is the active power. Reactive power also we can see the reactive power is 471.7, and apparent power factor and frequency. The power factor is also decreased due to inductive load. This is the output which we have displayed on the ThinkSpeak using Wi-Fi. So this is IT based. This is the VRMS and IRMS, and this is active power, and reactive power is zero. This is the result when we have connected 500-watt resistive load, and this is apparent power and power factor. This is the video demonstration of our project. You can see. This is the Arduino code which we have used to display the output on the LCD. Now applications are, we can say, the future work of our energy meter. This system can be used for power detection using IoT, and a right app can be opened option. This is option for online payment of bills. In this proposed method, load analysis of a single entity is performed, while in the future it can be used for area-wise load analysis, which will help full for load forecasting. These are the references by which we have collected data and to make our project possible. Thank you.